Good morning. Sorry I couldn't be there in person, but hopefully this will at least get you by. So what we're going to look at doing here is reviewing a little bit of the information that we started to cover yesterday on section 1.1 or 1-1, and we're going to just do a few example problems and get you into the homework assignment. Okay, some vocabulary from yesterday. We talked a little bit about this thing called inductive reasoning, and we said we define that to be a reasoning based on patterns you observe. Anytime you do inductive reasoning, you're usually going to get a list of numbers or some kind of picture or something of that matter. So let's say that for our purposes, we end up with some numbers that we need to make a inductive reasoning conjecture on. Let's say it's 1, 2, 4, 7, 11, and 16. So if we want to make a judgment on what the next number is going to be, we're simply going to call that a conjecture. So a conjecture is a conclusion you reach using inductive reasoning. And we did talk about we're not 100% sure, but we're pretty sure. So then you're going to do some things like look at rates of change and, are we doubling, tripling, are we subtracting, adding. So in this case, we'd look at this and say, all right, that goes up 1, that goes up 2, that goes up 3, and so on. And then this is an inductive reason patterning. I mean, we don't know that it's going to continue in this way, but we're going to assume that it will. So we're simply going to add 6 to that, and it's going to give me 22, and we could continue that on. All right, so let's take a different example. Let's say I said take a look at the first 3 odd primes. The first 3 odd primes are 3, 5, and 7. So if you didn't know what a prime was, you'd look at the pattern here and then you'd make your next conjecture and you'd probably would say 9 if you didn't know anything about primes. What do we call this 9? Well, this conjecture was wrong, so we called this before a counterexample. And the one thing that we said about counterexample is that it only takes one because we want to be 100% certain in math, and one of them screws it up, then this wouldn't work. And of course, you'd have to change that to 11, but that would be an example of a counterexample of a faulty inductive reasoning. We also mentioned this idea of deductive reasoning. We will revisit this concept at a later time. And like I mentioned before, just think of Sherlock Holmes. Basically what he did is he has a vast amount of logical reasoning skills. As a detective, he went through a lot of different cases, has a lot of background information, and then he made basically a specific conclusion from a bunch of general ideas. So we call that like a big to small versus inductive reasoning would be small to big. We also asked you to take a look at these 2 guided examples. I'm using the term guided because what happens in this workbook is they give 2 different types of examples. Ones where you kind of fill in the blank, and some that are just short answer. And once in a while we'll try these, and we won't do this all the time, but I'm going to read this with you. It says finding and using a pattern. Find a pattern for the sequence. Use the pattern to find the next 2 terms in the sequence: 384, 192. 96 and 48. Now this time we only have 4 terms, but you can see that they're going down and they're going down at a decreasing rate. Let's basically fill in the blanks here. They're saying, well, how do we get from 384 to 192 by division? Well, we divided by 2. It's half as big. We did the same thing to get to 96, and we did the same thing to go to 48. It's pretty safe to use inductive reasoning to make a judgment. So we can say each term is 1/2 the preceding term. So the next 2 terms are 48 divided by 2, which of course is going to be equal to 24, and 24 divided by 2, which is equal to 12. So pretty easy example. All right, let's check out the second example. It reads, using inductive reasoning, make a conjecture about the sum of the cubes of the first 25 counting numbers. Find the first few sums. Notice that each sum is a perfect square, and that the perfect squares form a pattern. So this idea of what we see here is going to be something you're going to see on a quiz, on a test, and definitely in the homework, but it's more of a direct application of why would you want to actually make these inductive reasoning conjectures. So what they want you to do is, instead of having to go through all this work, sometimes there's a faster way to do some sums or differences and such. So let's read a little bit further here, and you can kind of look at the patterns on your own. It says the sum of the first 2 cubes equals the square of the sum of the first blank counting numbers. So kids have kind of struggled a little bit with this in the past, but really what you want to look at is if you look at this number and how it connects with this one, how these two connect with this, and these two connect with this. It's more or less they're showing you a shortcut. So what they wanted you to notice on this one is if you want to cube 1, it's the same thing as 1 squared. If you want to add 1 cubed and 2 cubed, it's the same as 1 plus 2 squared. If you want to add 1 cubed, 2 cubed, and 3 cubed, it's the same thing as 1 plus 2 plus 3 squared. And you can see that pattern continues. So when it says the sum of the first two cubes equals the square of the sum of the first blank counting numbers, it has to match, right? So we're going to use this number in that location. Then it just repeats itself. The sum of the first 3 cubes equals the square of the sum of the first 3 counting numbers. This pattern continues for the 4th and 5th rows. So a conjecture might be that, and so they essentially want you to continue to write what a conjecture for this situation. Okay. Everyone's going to have something different, but what I think is, why don't we go big? You can probably do both of these things fairly easily, by hand, but let's see what happens when we increase the amount of numbers. So let's say that I wanted to do the first, instead of 5 or 6, let's say we wanted to do the first 25 instead of stopping at the number 5. What would that look like? Well, I'm going to write this in a little different notation, but if I wanted to go 1 cubed plus 2 cubed plus 3 cubed, I'm not going to write all these out, so I'm going to go plus dot 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 plus 24 cubed plus 25 cubed. That may be a lot of work, but my conjecture is this. I think following the pattern that we have in this location right here, what we should be able to do is take 1 plus 2 plus 3 and kind of keep going with that idea. Add up 24, add up 25, and then simply take that and square it. That's my conjecture. And yours may be different. All right, so I think we're done with the workbook. If you guys want to go ahead and put those aside, and I'd like you to take out your notebook for this. In your notebook, if you could, what we're going to do is just a few quick examples, then we're going to get you going on your homework assignment. And what I'd like you to do is, I'm not really interested that you necessarily write all the questions down, especially the directions. I'm more interested in, can you answer the question? So this is how this question reads. It says, find a pattern for each sequence. Use the pattern to show the next 2 terms or figures. So essentially, what's that one and what's that one? Okay, so if you want to go ahead and pause the movie, let's give people a chance to answer this question and see what we get. Okay, here's my inductive reasoning. It looks to me that I'm multiplying here by -2. To get from -6 to 18, I'm multiplying by -3, and I'm multiplying by -4, and multiplying by -5. That's what seems to be happening. So I think what I'll do is just kind of continue that same idea and fill in the next 2 blanks. All right, so we'll continue that pattern. I just multiplied 360 by 6, with technically -6. So don't forget the negative number. I've got negative 2,160 for that value. And then I just multiplied that number by -7. So 2,160 times 7 would give me a positive 15,120. Okay, pretty basic stuff. Yeah, we can tweak this idea a little bit. Again, what we'd like to do is have you guys do the next 2 in this pattern. Instead of numbers, we're going to go to figures this time. So let's give it a pause and give it a shot. Hey, lots of different ways to interpret this, but if you just think of it from a visual perspective, we've got 1 division, 2 divisions, and we kind of keep going from that. So we're going to increase the number of vertical lines is one way to look at it. So I'm going to go ahead and split this up like this. Not the straightest line ever, but we can make it work. And then we're going to break this up into more or less 5 rows, 5 columns. Okay, not fancy by any means, but it serves the purpose. Another way you can think about it too is you got 1 square, you've got 4 squares, 9, 16, and 25. remember that another way to look at this is essentially a model of the perfect squares. Alright, so this one says use the table and inductive reasoning. Make a conjecture about each value. So again, this is a way that you can kind of take a look at large amounts of numbers being added, and if there's a shortcut. So you can see it. We're going to start with 1, then 2, then 3, then 4 numbers, and if we increase that, what happens? Now, number 3 says, what's the sum of the first 10 counting numbers? So right now, this right here would represent 4 numbers, 3, 2, and 1. And what I want you to do is look where that number shows up. This 1 shows up in this position. The 2 shows up in this position. The 3 right here, and the 4 right here. So let's finish this thing off. What they were hoping that you'd see based on that pattern is if you have 10 counting numbers, all you have to do is take that number, multiply it by the number 1 larger than that, and then just divide that by 2. So 10 divided by 2 is 5. 5 times 11 is going to give you 55. Alright, number 4, again, you could still do number 3 by hand. Number 4 is a different story, right? So for 1,000 counting numbers, you're going to take 1,000, you're going to multiply it by 1,001, and then you're going to divide that number by 2. Alright, do the math. You end up with 500,500 for number 4. Last example, and then we'll get you going on the homework. It says show that the conjecture is false by providing one counter example. This one says the sum of 2 prime numbers is an even number. So let's go ahead and hit pause. Let's try to come up with at least a few different ones. The sum of 2 prime numbers is an even number. Let's find a counterexample. Well, it helps if we have a list of primes. We're going to go 2, 3, 5, 7, skip 9, go to 11, 13, 17. It's probably good. Let's try it. Let's just take the first 2. 2 plus 3 is 5. 5 is not even. There's my counterexample. You can try 3 and 5. 3 plus 5 is 8. 5 plus 7 is 12. 7 plus 11 is 18. These even give you 24, but the 2 plus 3, even right off the bat, isn't going to give me something that's even. So there's my counterexample. All right, hopefully that's enough information to get you going. So if you could please take out, I guess we can probably just leave this on the same page. So at the top of your piece of paper, what I'm going to ask that you do is just make sure to label this homework section 1.1 or 1-1, however you'd like to say it. And then here are the problems. I'd like you to put all that information right here at the top of your paper so you can record this for later. But we'd like to work on page number 6, numbers 17 through 26, 31, 32, 36, 46, 52, and 54. The answers will be provided at the front table. We'd like you to work on this individually and then kind of check answers as you go, and we'll even maybe have some time to answer some questions at the end of the hour. If not then, definitely tomorrow. And again, sorry I couldn't be there for you guys. Hopefully you had a good hour.